Matrix methods for linear systems, and in this section we will be talking about homogeneous linear systems with constant coefficients. So in this section we're going to focus on finding a general solution for this homogeneous system. And A, of course, is our constant n by n matrix. And of course, those are real constants. So we are going to use a similar method that we had in the past when we solved homogeneous linear equations. And at that time, we had the form e to the RT. So let's go ahead and take a look at this definition. Let A be our n by n constant matrix, and the eigenvalues of A are those real or complex numbers for R, which A minus Ri, all multiplied by U, is equal to 0, has at least one non-trivial solution U. The corresponding non-trivial solutions U are called the eigenvectors of A associated with R. So let's take a look at this below. Our characteristic equation of A, of matrix A, is shown as the determinant of A minus Ri, and of course we have that set equal to 0. Keep in mind that a linear homogeneous system of n equations and n unknowns has a non-trivial solution if and only if the determinant of its coefficients is 0. So we can now expand the determinant in terms of cofactors, and we can see our characteristic polynomial of A, and that's our nth degree polynomial in R. So right here, that's our nth degree polynomial in R. And we call this our characteristic polynomial. Let's jump right in and try one of these here. Eigenvalues and eigenvectors of this matrix. We will first solve the characteristic equation. So we'll take the determinant of A minus Ri, and we have the determinant of this matrix, and we have that is equal to, and of course we can write -4 minus and similarly, and then it's just, we'll multiply those like that. So of course we have 4 plus R multiplied by 1 plus R, and then we have minus 4, and let me just erase that. Of course we have R squared plus 5R, and then of course we have plus 4 minus 4, so we end up with R multiplied by R plus 5. Therefore, we have eigenvalues R equal to 0 and R equal to -5. So now let's find the eigenvectors associated with these eigenvalues. So for R equal to 0, we will have and here we have U1 and U2 are U vector. And then that gives us 4U1 plus 2U2. And then our second row, 2U1 minus U2. And that is equal to 0. So this implies that 2U1 minus U2 You can see that second row is equal to 0. So we're going to find just arbitrary value for u sub 1. So let's go ahead and just take u1 equal to s. And of course, if u1 is equal to s, then u2 is equal to 2s. And you can see that right here from this equation. So now we can go ahead and come up with u1 is equal to s, 2s, and we have s times our vector 1, 2. Okay, let's go ahead and take a look at when we have r equal to 5. We have, you can see from this characteristic equation here that when r is equal to 5, that should be a negative 5. Of course, we'll be plugging that r into there, and we have a matrix 1, 2, and 2, 4. Oh my goodness. And of course, now we will multiply by our u vector, and that gives us u1 plus 2u2. And then we have 2u1 plus 4u2. And of course, that's equal to our 0 vector. So we have u1 plus 2u2 is equal to 0. So if we go ahead and let u sub 2 equal s, then of course if u sub 2 equals s, we can see that u sub 1 is going to be equal to negative 2s. That kind of looks funny there. Whoops. Okay, so now we have u sub 2 is equal to vector u sub 2, negative 2s, and that's equal to s multiplied by our vector, negative 2, 1. So the eigenvectors that are associated with r equal to 0 are shown here, and the eigenvectors associated with r equal to negative 5 can be expressed like this. Okay, problem is again to find the eigenvalues and eigenvectors of the matrix, and let's go ahead and begin with the characteristic equation for this matrix. So we have the determinant of A minus Ri, and we have that that's equal to 1 minus R, and of course we'll have 0 here, and 0, 0 negative R, and 2, and 0, 2, and negative R. And we have that that's equal to 1 minus R multiplied by the determinant, negative R2, 2 negative R. And then we have that that's equal to 1 minus R multiplied by R squared minus 4. And let's go ahead and factor that. 1 minus R, R plus 2, R minus 2. And of course we have that that's equal to 0. And so the eigenvalues are R equal to 1, 2, and negative 2. Let's begin with R equal to 1. And here when we substitute that into our equation, a minus I times u, we have, here's our matrix, multiplied by our U matrix, and we have that that's equal to 0. And we have that that is equivalent to the system negative U2 plus 2U3 is equal to 0, and 2U2 minus U3 is equal to 0. Here, the system reduces to U2 equal to 0 and U3 equal to 0. So we do not, we're not given any value for U sub 1. So let's go ahead and let U sub 1 equal S. This is just an arbitrary value S. And of course, U2 equal to 0 and U3 equal to 0. So now we see that the eigenvectors associated with the eigenvalue r equal to 1 are given by which is equal to s times our vector shown here. Okay, so now let's go ahead and take a look at our eigenvalue r equal to 2, and we can see that we have our a minus I times u is equal to, and we'll just go ahead and create that matrix. Of course, we have our u's. And now this system of equations reduces to u1 equal to 0 and u2 equals u3. You can see that here. You can see that negative u1 is equal to 0. In the next two equations, we have negative 2u2 plus 2u3 is equal to 0. So of course we can see here that u1 is equal to 0 and u2 is equal to u3. So we'll go ahead and introduce our arbitrary value. So we'll go ahead and let u sub 2 equal s, and that gives us u sub 3 also equal to s. And let's go ahead and find the eigenvectors for this matrix associated with the eigenvalue r equal to 2. We have that u2 is equal to u1 and of course we have s times our vector 0, 1, 1. Okay, how about for r equal to negative 2? We'll go ahead and solve this equation, a minus I multiplied by u, and now we have our matrix. Whoops, I can see that I made a mistake right here. This should have been a minus 2i. And of course now we have a plus 2i. Let's go ahead and write that out. So we have 3, 0, 0, 2, 2. Of course, multiplied by our u vectors is equal to 0. And so this equation, the equations, we could write 3u1 is equal to 0 and 2u2 plus 2u3 is equal to 0. And of course now we have that u sub 1 equal to 0 when we reduce those, and u sub 2 is the opposite of u3. Since u sub 3 is arbitrary, let's go ahead and let u sub 3 equal to s, and that means that u sub 2 is equal to the opposite of s. So now we can write our eigenvectors associated with our eigenvalue r equal to -2 as u sub 3 is equal to u vector, which is equal to this. This should be a -s. And now we have s multiplied by our vector 0, -1, 1. Okay, so for our next example, we are going to find the eigenvalues and eigenvectors of this matrix. So we have that the determinant of A minus Ri is equal to the opposite of R, -1, 1, and -R. And we can see that that's equal to R squared plus 1, of course, which is equal to 0. So we have that our eigenvalues are R1 equal to I and R2 equal to -I. So for R1 equal to I, we have our matrix 1 and -I multiplied by our U matrix, which is equal to 0, 0. So our determinant here of A minus Ri gave us those two eigenvalues. For R1 equal to I, we now can see that U1 minus IU2 is equal to 0. So if we let U2 equal S, then U1 is equal to IS. So we have that eigenvectors associated with our eigenvalue of I is equal to ISS, which is equal to S multiplied by the vector I1. Now, keep in mind that R2 is equal to the complex conjugate of R1. So that means that U2 is equal to the complex conjugate of U1. So we could just say that U2 is equal to S multiplied by the complex conjugate of vector I1, which is equal to S multiplied by -I1. Okay, and that is our eigenvector associated with R equal to the opposite of I. Okay, let's talk about linear independent eigenvectors. Linearly independent eigenvectors. So the question is, can we obtain n linearly independent solutions to the homogeneous system by finding all of the eigenvectors and eigenvalues of A? The answer is yes, if A has n linearly independent eigenvectors. Okay, so taking a look at this theorem, suppose we have our n by n constant matrix A and we have n linearly independent eigenvectors. And here they are. And let R sub I be the eigenvalue that corresponds to each eigenvector. Then this set is called a fundamental solution set. And x of t is equal to this matrix, and we call that our fundamental matrix on negative infinity to infinity for our homogeneous equation, homogeneous system shown right here. Consequently, a general solution, x prime equals ax, is shown as x of t equals. And you can see here that we have arbitrary constants and we have our eigenvalues, e to the r1t and e to the r2t and so forth. So let's give this a try. Let's find a fundamental matrix for this system, x prime of t equals ax of t, and we are given matrix A. Actually, I have the wrong wrong matrix here. And let me go ahead and use matrix A as this matrix 0, 1, 0, 0, 0, 1, 8, negative 14, and 7. Okay? So we will omit this matrix that was written there. Okay, so we first have to find our eigenvalues for the matrix A. But we do see that for this system, since it has 3 columns, which are linearly independent solutions to the given system. We will first solve the characteristic equation. So the determinant of A minus Ri is going to be equal to, and I'll just go ahead and get that written down. And we have that that's equal to 0. And let's go ahead and compute that determinant. And of course, that's equal to 0. I went ahead and did some of this algebra, and I will go ahead and put a star there so that we end up with r cubed minus 7r squared plus 14r minus 8 is equal to 0. And so factoring that, we have r minus 1 multiplied by r minus 2, r minus 4 is equal to 0. So we have 3 distinct eigenvalues. So we have 3 distinct eigenvalues. And those are r equal to 1, 2, and 4. So these eigenvectors that are the eigenvectors that are associated with these eigenvalues are linearly independent. So these eigenvectors can be used to find 3 linearly independent solutions. Let's begin with eigenvalue r equal to 1. And of course, we will have a minus u, a minus I multiplied by u. is equal to 0. So we'll go ahead and find that. And we have this matrix. Of course, multiplied by u. And that's equal to our 0 vector. And so now we have that this must be equal to 0. So we will we can see that u1 is equal to u3 and u2 is equal to u3. So if we let u3 equal 1, we can see that u1 and u2 are also equal to 1. So now we have eigenvector associated with the eigenvalue r equal to 1 can be given as 1, 1, 1. Okay, let's go ahead and find an eigenvector associated with eigenvalue r equal to 2. We will go ahead and solve a minus 2i and I think I had, yes, that was right, a minus 2i, and let's go ahead and write that out, multiplied by u. And here we have, and reducing that matrix, we have 4, 0, negative 1, and so we have the system shows that u1 is equal to, 4u1 is equal to u3 and 2u2 is equal to u3. So we are given this system. So we could say that u3 equals 4. Then we have u1 equal to 1 and u2 equal to 2. So the eigenvector associated with our eigenvalue r equal to 2 is 1, 2, and 4. Okay, let's go ahead and find the eigenvector corresponding to the eigenvalue r equal to 4. So we have, and I might go ahead and move that down here. And we have our equation a minus 4i multiplied by u. We have this matrix. And now, reducing that matrix, we have 16, 0, 0. So now it gives us a system of equations. 16u1 is equal to u3, and we can see that 4u2 is equal to u3. So if we let u3 equal to 16, then we have that u1 is equal to 1, and u2 is equal to 4. So therefore, our eigenvector associated with our eigenvalue of 4 is equal to the vector 1, 4, 16. So we see now, because of this theorem right here, we see now that there are 3 linearly independent solutions to this system, and they are given, and I'll go ahead and write these down. So therefore, there are 3 linearly independent solutions to the system. And these are e to the t u1, e to the 2t u2, and e to the 4t u3. So let's go ahead and create our fundamental matrix. And we have e to the t in our first column, and our second column, e to the 2t, 2e to the 2t, and 4e to the 2t. And then our third column, e to the 4t, and of course our derivatives, again, below. And that concludes this video.